All right. We are now at the final talk of the session, or the day as well. Oriel is going to talk about ground state algorithms now.
Hello, thank you for sticking with me until the end of the day. I know it's been a long day and a lot of great technical talk. So I wanted to take like a more practical approach about early fault-tolerant quantum algorithm and not give a lot of, calculations, but more delve into like practical issues and how to tackle them. So we are all here because we want to solve useful problems on quantum computers, I guess. And for now, what you, like our bet is, we hope there is something to do, right? Our bet right now is on quantum spin system because they're quite, we can map them to quantum computers quite directly and take advantage of, computers bound to have great Hamiltonian simulations. I think we can classify quantum algorithm in like two different paradigms. The first is like NISQ, where you have mainly versional stuff with like no guarantees and with bad scaling. On the other hand, you have fault-tolerant quantum computers, and here you have quantum phase estimation and friends. And there you have a great scaling, but it's also quite scary to build this on an actual machine. And what you want to look at today is like what's in between. So to have some kind of computer that you can trust, but you don't have like infinite depth or infinite width, so you have like kind of restricted resources, but what you want is to trade, the depth with more samples. And that's the kind of algorithm we want to look into today. So maybe NISQ is a bit dead, but we hope that not too far away we can still do something interesting. So first I want to present a bit the linear-tongue algorithm. So there is a broad class of those type of algorithms that have been proposed, and they're basically all working in the same way, which is why I'm focusing on the first one. So you have given an Hamiltonian, and you want to find ground state energy, right? And you want an algorithm which has nice properties, such as having few ancillas, so ideally 1, which has also low depth, ideally 1/epsilon, but for this kind of algorithm, we'll see that it's more 1/epsilon squared. And finally, you want to have something which is a bit robust also against error that you can make, like doctorization error or shot noise error, stuff like this. So how does it work? So it's basically, you want to answer a binary question. So you can imagine that you have your energy on the line and you want just to decide if at a given point, your initial state rho that you have to give as input to your algorithm has zero overlap on the eigenstates on the left or a non-zero overlap. And if you can find the exact point where this goes from 0 to non-zero, then you find your ground state. So the way you can do it is just build the cumulative distribution function of your spectral measure. And if you do this, then you're going to get a step function like this, and the height is like directly dependent on the overlap between your initial state and the true ground state. And here the width is depending on the approximation of your CDF, so how you're building this. If you want more detail, it's quite straightforward. What you can do is to take your favorite filter. So here the Heaviside function, you write it as a Fourier series. Then you convolve it with a spectral measure, and if you do this, you will get something like this with some coefficient f that you can compute analytically, and some Fourier moments on the right that you can compute on a quantum computer using some simple Hadamard test or something like this. And then in the end, what you want to do is just sample time indices, run a one-shot estimator on a quantum computer, add everything together, and you get an unbiased estimator of your CDF. And if you do this, then you can rebuild this CDF, find the steps, and you're done. So amazing, right? This is exactly what you want to do. And then we go into more practical aspects, and there is a lot of challenges that you might a bit forget when you think about this on a theoretical level. And the first one for me is really initial state preparation. So usually people assume you can get initial state with a lower bound eta on the overlap, which is great to prove things, but in practice it's like difficult to build those states. So how do you do this? Second thing, the overlap also is something important, because if you want to know that your step is larger than eta, then you need to know eta, but it's also difficult to estimate it. So how do you deal with this? Then finally, Hamiltonian simulation, which technique do you want to use, and the prefactor, like, is it worth it to think about this algorithm, which like not an optimal scaling? Is it worth it for near term or not? Okay, so let's try to answer these questions. First one, initial state preparation. So maybe it's a bit trivial what I'm going to say, but I think we have great methods out there from the classical methods, and I think we should use the best that we can, like GMG, cover clusters. So we don't, for me, they are not like, enemies to do better, but we should use them and try to improve upon what they give us. The overlap, I think here, like the way we are trying to think about this algorithm is a bit different from what was originally proposed. So instead of trying to really find the true, like the first ground, so the ground state exactly, we are trying to find the inflection point of the CDF. So like the point where you can be confident with some probability that you're above zero. And like a way to do it is to estimate the empirical noise. So if you look at a segment where you have no eigenvalues, then the signal should be zero, but you can measure like some standard deviation. And then if you take this and you can find the first point which is above this. So this is not going to be the ground state, but this is going to be really close. And this is like the paradigm shift we want to propose. This has also to do with like a kind of an accumulation like point of view. Like instead of trying the first state, like so if you have like m equal to 1, this is like eta for the true ground state, but we want to look at the low-lying energy regime. And this is also what we want to use the step function, because if you have like, the first few excited states are going to add to a bigger step, which is more easier to detect than a single step. And if you use like another filters, like for example, Gaussian kernels, which are also great, but the Gaussian kernels, so you are going to get like peaks at the different eigenvalues. And if, the peaks are far apart, then you're not going to get this accumulation effect. Okay, Hamiltonian simulation. This is really difficult. I don't really want to give an answer for every system. I can't. But what we think is that if you have like a really structured like model, like a spin system, then trotterization is still going to be competitive. And if you look at like the paper from Childs and other a few years ago, they show that empirically trotterization is still pretty competitive. Also, you don't need any ancilla. You don't need a lot of complicated operation that takes space on hardware. So they have a lot of good properties. And finally, also, if you at fixed time and fixed epsilon, they also scale better than quantization for some system. Like if you take Heisenberg model, you can show that the dependence in n is like better than for quantization, even if it's not better for t or epsilon in n, it's still better. So in some regime, you might be better off using trotterization. Okay, so this is like the general framework of this kind of algorithm. So really briefly, you have initial state that come on the left, the Fourier coefficient on the bottom here, you sample time, you do one shot estimator of your Fourier moment, and then you add everything up, you have the CDF, and then you're going to find like the inflection point by using like a binary search. So you want to find like, I'm going to talk about this in the next slide, but like you can segment your signal into two, find the breakpoint, then take the left part and go on and on until you're done. And then you want to verify that the step is statistically significant using some test that you can do. And once you're there, you're just going to compute the gradient of the CDF, which is a bunch of peaks, and then you get the middle of the peak, and that's going to be your estimate. Okay, so I guess we got a few insights from our study, and like the first one for me is really that is great. So if you look small system, right? So that's what they showed in the first papers, is you see the step really clearly, and by eye you can say, okay, this is my ground state, and I'm done. Of course, in real life, if you do like more complicated system, this is going to look like more like the red curve, which is much more continuous. And here, either you have to zoom in to find the steps, or you cannot really look by eye. So it would be great to have like an automatic procedures. And for this, what we do is that we are breaking the signal into two, using like minimizing some kind this loss function. It's a convex problem, so it's easy to do. And then like if you have a signal like this, and you find in the middle, you find the breakpoint, then you take the left part, right? Do it again and again, and at some point you're going to do a break, which is like not significant, and at this point you can do a statistical test that's just comparing the variance of both segments, and this is going to be lower than some probabilities, and then you just reject the step. The second insight is more like quantitative resources, so how many samples do you need to detect a step. So the depth, maximal runtime of the algorithm is like dictated by the free decomposition of the filter, right? So this is like you're just using the decomposition by Campbell, so we know that maximal runtime goes as 1 over delta. And then the number of samples that is required to detect a step of size eta goes like this. So basically it's 1 over epsilon squared, so that's what you would expect just from statistics. Maybe what is interesting is to look at the dependence between m, eta, and at a fixed epsilon. So basically what this plot is telling you is that if you want to detect like a step of size eta, so on the y-axis, then you can do it by increasing m, right? But at some point it's going to plateau, right? So at some point it's like useless to just sample more and more. At some point, if you want to have better resolution, you need to increase the depth, and that means increasing, like having a better approximation of your step function. So you cannot win forever just by sampling more, but there is like a trade-off. Okay, and like also something that we like from a user perspective. So the eta, this is like the estimate on the overlap, right, which is not always available. But I think the way to think at it from a more practical point of view is like this is like a user, like depending on the resources that you have. It's more like, okay, how many shots do you have? And this is like this resolution eta that I can hope to detect. That's like, I think from a practical point of view, you have to shuffle the prime around. Okay, so I think we have enough of this. We want to see how this performs. So what you're taking here is a simple Heisenberg model, fully connected, random couplings with 26 spins, if I remember correctly. We want something which is like challenging for geometry. This is why we take also fully connected model. And then for the dynamics, we use simple totalization using a subnetwork. So I know there is a lot of great techniques out there. We could have used QDIF, could have used multi-party formula or anything, but we wanted that was not really the point. We really wanted to just to give like practical, address the practical challenges. Okay, so the initial state, as I said before, we take geometry with like a low bond dimension, and the hope is that from a low bond dimension you can extract high bond dimension solutions. Okay, so there is like a lot of different subplots. So maybe the 3 different colors are basically different number of samples from 100 to 10,000. And the top line you have the CDF. In black you have the infinite, like the result with infinite statistics. Then in the middle line you have a zoom inversion around like the first step, and on the bottom one you have the gradient. So this is going to be a bunch of peaks. And there is like different interesting stuff that we can see from here. So the first is so the colored line, the colored vertical line is what you get with our signal processing techniques, so by just segmenting our signal. The dotted line are the geometry result, and the one here, so this line here is basically what you get from the initial state. So we can see that even with the initial state with like this energy, we can improve by like 5%. So it's already a win. Secondly, this is like just the dependence on the energy with respect to the number of samples and the maximal depth. So we did like a study where you just truncate the depth and the number of samples, and we see what happened. And what we understand is, okay, if you increase the number of samples, at some point you plateau and it's useless to go beyond. But for the depth, you still need to have like a minimal amount of depth. Like if you have like the yellow one here, you're never going to reach the true ground state even if you sample more. So you need still a minimum depth, which is quite, from what you get from the estimate from Campbell, it's quite close, I would say. So you cannot really truncate it that much. And like the last thing which is interesting is that if you look at the overlap between the initial state that you get and the proxy for the true ground state, so like the converged geometry, you have like an overlap of 10⁻⁶, which is small. And if you hope to detect it, then you need like 10 to the 13 samples, right? So this is like really much. But if you only care about detecting like this first inflection point, so like the first non-zero point, then you can get away with 10 to the 3. So in practice, you can get away with like a really few samples. Okay, so this is the same experiment. Instead of use a bit worse initial state, so we just pacify it, so keeping like the 10 largest components. And the goal of this is really to trying to understand what would happen if you have like a more complex system. And then the MG is maybe not that good. And here what happened is that you don't have the steps, so you either have like a continuous line, right? And if you want to see the steps, you have to zoom in like here 0.02, so it's like you need more samples. But still here you can like have like a 30% improvement, so like this is what you get from the MG, and like using only 10 to the 5 samples, you can get pretty close to the true ground state. So okay, so the initial state is worse, you need more samples. That's basically what it tells you. And that's also what it's saying. So it's like the same result from before, but like worse initial state, then you need more samples. The depth is like the same as in the other study. Okay, so maybe to conclude, this LT algorithm and friends, they bridge the gap between what you have now, NISC, and what we could have in the future. So they're like, I mean, those kind of algorithms for me, they are like quite cheap, so you can get away with a few samples and you can still get like reasonable estimate. The issue is that if you want to have like really precise energy, like maybe in chemistry you want chemical accuracy, then what you want is more using quantum phase estimation. So, like the conclusion is this is a really cheap algorithm if you want crude estimate, like good but not like 10 to the minus 10 good. But if you want 10 to minus 10, then use something which has 1 over epsilon scaling, which is doing like QPE or K2 or stuff like this. Yeah, so the paradigm shift that we propose is to look at this inflection point instead of the first step, which is really difficult to detect in practice if it is small. And also trying to look at this algorithm as a way to improve on classical estimates and not just as a competitor to the MG. So try to join forces here. So yeah, as I said, QP is much better if you want a really good approximation, but if you don't care that much, like maybe in another field like nuclear physics, you don't really care about having amazing precision, this is like a really good algorithm for these situations. Yeah, so as I said before, should join forces, not try to see classical versus quantum, but classical and quantum. And if I have more time, I would like to, yes, just to present a short experiment on IBM devices. So the only thing we need quantum computers for here is computing Fourier moments. So like overlap between the initial state and the time evolving initial state. So here it's pretty easy to just using this. You can just do a Hadamard test. So you just need to do controlled time evolution. Okay, so this is like a study from people from Riverlane, where they did this on a 6-qubit molecule. What we're doing here is just taking effective field theory, so something just like a triton on a 2x2 lattice. And what we're using is preferred echo verification to do error mitigation. So preferred echo verification, really short, you prepare your state, you do your Hadamard test using the ancilla, and then you unprepare the state, and you project on 0, right? And if an error occurs, then you won't get back to 0, so you can like know that something bad happened. And then what you do is that you just throw away everything that doesn't pass verification. On top of this, you know that the ancilla is pure if pass selected on 0 state, and so if it's not pure, you can just purify it, and this should get you closer to the correct result, right? And so if you do this, then the first thing is, okay, we look at noise model, right? So taking IBM noise model. So the thing to look at here is, so you have the error compare as a function of the noise, right? And the purple line is like without error mitigation, and the red one is with preferred echo verification. So here you can get like a 100 improvement, so you can still like improve on your computation. And Now you go to real hardware and you see what happened. And this is like just doing control time evolution. So here we cheat a bit. We don't want to have like control time evolution. We do like control result gate to avoid doing control because otherwise it's too expensive. But we do tricks like this. And here, if you have like without an error mitigation, you get only like a line at 0, which is meaningless. But with perfect echo verification, you can have pretty decent signal up to like 250 C0, so like 8 charger step. And finally, which is also neat about this technique, is that if you look at the purity of the ancilla, so this is something which is going to be bounded by 1 and 0.5. So you know that when the purity of the ancilla is going to be 0.5, then when you're going to purify it, you go 50-50 into both directions. So you cannot trust your purification. And indeed, what happened is that on those two last points, the results are like, they have a huge error buffers because you just go randomly, and they are far off. So you can get a way to like know if your quantum simulation was successful or not. With this, I would like to thank you for your attention, and happy to answer any questions.
Any questions?
Thank you for your nice talk. So you started from DMRG solution. So starting from some kind of classically optimized solution requires quantum circuit representation of that solution. So is that DMRG solution is easily implementable as a quantum circuit?
Yeah, you can do it in poly time in the bond dimension, so it's not a problem.
Okay, thank you.
To estimate the Fourier moments of the Hamiltonian spectrum, you need to make sure you start with a state that has like good enough overlap with the entire spectrum, right?
So you mean in the IBM experiment, or in general?
I think in general in the Lin
so
approach.
For the 26 qubit, I didn't check the overlap with the whole spectrum, so I don't know. What I do know is what is the overlap with the first, right? It's 10 to the minus 6. This I know. The rest, I have to say, it's a huge calculation.
Okay, thanks.
But yeah, so like if your initial state has like an exponential support, then you're going to get like a smooth function. So you see in the first experiment, you have 2 steps. So this is clearly a sign that you have the contribution like localized, right? And then after that, you had like something which is much smooth, which means that you have support from anywhere. So I'm guessing that on for the first, you have like, I guess, a few peaks at the beginning, and then it just decays. And then on the second one, it was much more smooth. I guess you have something which is more spread out. But I didn't do the calculation.
All right, let's thank Oriel and all the speakers from today.